Drone hunting tech, why it's more science than sport in 2026. In 2026, drone hunting doesn't look like people chasing flying machines through the sky. There are no binoculars, no dramatic pursuits, no physical battles. Instead, it happens silently, invisibly, inside radio waves, thermal photons, pressure gradients, neural networks, and mathematical prediction engines operating faster than human thought. This is not hunting in the traditional sense. This is physics hunting physics. Every modern drone is a moving equation. The moment it lifts off the ground, it becomes part of a massive scientific system involving aerodynamics, electromagnetism, heat transfer, artificial intelligence, and atmospheric sensing. What looks like a small flying object is actually a cyber-physical platform carrying processors, inertial sensors, radio transmitters, thermal sources, and autonomous decision logic. And detecting it is no longer about eyesight. It's about understanding reality at the level of electrons. Lift itself is governed by pressure differentials. As air flows over spinning propellers, velocity increases on one side and pressure drops on the other, producing upward force described by Bernoulli's principle. Even a lightweight drone must continuously solve Newton's laws of motion. Force equals mass times acceleration. Every micro-adjustment of pitch and roll requires onboard computers to calculate torque vectors hundreds of times per second. Inside a typical 2026 drone are MEMS gyroscopes vibrating at tens of thousands of cycles per second, accelerometers measuring changes smaller than 1,000th of Earth's gravity, barometers sensing altitude shifts of less than 10 centimeters, and magnetometers detecting subtle distortions in Earth's magnetic field. These sensors feed into sensor fusion algorithms, mathematical systems that combine imperfect data streams into a single estimate of position and motion. This process uses Kalman filtering, a probabilistic model that predicts future states while correcting itself with incoming measurements. That means every drone is continuously predicting its own future. Now imagine trying to detect that. By 2026, drone hunting begins in the electromagnetic spectrum. Every electronic device leaks energy. Motors emit harmonic noise. Digital radios broadcast packets. Switching regulators create RF spikes. Even onboard processors radiate microscopic electromagnetic signatures. Nothing electronic is perfectly silent. Advanced detection systems scan frequency bands from 300 MHz to over 6 GHz, watching for characteristic modulation patterns. Each drone protocol has a distinct spectral fingerprint, timing jitter, phase noise, symbol structure. Artificial intelligence models trained on millions of signal samples can identify these patterns in under 100 milliseconds. This is signal intelligence without humans. Even autonomous drones that transmit nothing still betray themselves. Their electronics emit unintended radiation. Their rotating motors generate electromagnetic interference. Their power systems create rhythmic noise signatures. Physics always leaves a trace, but RF is only one layer. Thermal imaging adds another dimension. Electric motors convert electrical energy into mechanical motion, but efficiency is never perfect. Roughly 10-20% becomes heat. Lithium batteries warm under load. Control boards heat unevenly. Infrared cameras operating in the 8-14 micrometer wavelength band detect temperature differences as small as 0.03 degrees Celsius. From several kilometers away, AI systems can see a drone's thermal skeleton, and unlike animals or birds, machines heat symmetrically. That matters. Then comes acoustic sensing. Rotating propellers generate pressure waves in the air. These vibrations propagate at the speed of sound, about 343 meters per second. Microphone arrays spaced meters apart capture arrival time differences measured in microseconds. Using triangulation, software reconstructs the source location. Each propeller produces a unique harmonic spectrum. Blade count, RPM, and motor type create acoustic fingerprints. Neural networks identify these patterns instantly. Bird wings flap irregularly. Drone propellers rotate with precision. Physics again reveals the difference. Next comes radar. Modern drone detection radars operate in X-band and Q-band frequencies between 8 and 18 gigahertz. At these wavelengths, resolution drops to centimeters. Phased array antennas electronically steer beams without moving parts, scanning entire volumes of sky in milliseconds. But here's the key advancement: Micro-Doppler analysis. As propellers spin, they create tiny frequency shifts in reflected radar waves. These shifts form spectral signatures that AI models recognize. Even when a drone is stationary, its rotating blades betray it. This allows discrimination between drones, birds, debris, and weather. But radar struggles at low altitudes, so scientists turn to passive radar. Instead of transmitting signals, passive systems listen to reflections of existing broadcast sources, cellular towers, TV transmitters, satellite links. By comparing direct and reflected signals, systems calculate time delays and phase shifts to locate airborne objects. This creates detection without emission, invisible sensing. Then comes LiDAR. Pulse lasers at 905 or 1550 nanometers scan airspace, generating 3D point clouds with millimeter precision. These optical systems map object geometry in real time, feeding shapes into classification algorithms. Every sensor feeds into a central fusion engine. This engine doesn't just detect, it predicts. Using kinematic equations, machine learning models forecast trajectory seconds ahead. Position equals initial position plus velocity times time plus half acceleration times time squared. But in reality, thousands of variables modify this equation: wind gradients, control responses, battery voltage, payload mass. So AI learns patterns. By 2026, systems trained on billions of flight hours can predict drone movement with over 90% accuracy several seconds into the future. This is not reaction. This is anticipation. At this point, drone hunting becomes mathematical choreography. The system watches acceleration curves, hover stability, turn radius, vertical oscillations. Each behavior reveals autonomy level. Human-controlled drones move differently than AI-guided ones. Machines fly clean. Humans wobble. That distinction matters. Meanwhile, encrypted communications complicate everything. Modern drones use frequency hopping spread spectrum, jumping channels hundreds of times per second. Advanced receivers sample gigahertz wide bandwidths, reconstruct hopping patterns, and analyze packet timing. Even encrypted links reveal metadata. Timing tells stories. Power fluctuations reveal distance. Phase noise exposes hardware. Nothing escapes physics. Edge AI processes all of this locally. Instead of sending raw data to cloud servers, inference happens inside cameras, radars, microphones. Latency drops below 20 milliseconds. That's faster than the human nervous system. Now imagine hundreds of sensors forming a distributed nervous system across a city. Buildings become nodes, towers become eyes, streetlights become ears. Everything senses. This creates low-altitude airspace maps updated dozens of times per second. Digital twins simulate environments, solving Navier-Stokes equations for airflow and Maxwell's equations for electromagnetics. Synthetic drones fly through virtual cities millions of times per day, training AI to recognize every possible pattern. Reality becomes rehearsal. By 2026, photonic processors begin entering experimental platforms. Instead of electrons, these chips compute with light. Fourier transforms that once took milliseconds drop to microseconds. Spectrum analysis becomes nearly instantaneous. Metamaterial antennas reshape radio waves. Graphene infrared sensors detect single photons. Neuromorphic chips process spatial data using brain-inspired architectures consuming fractions of traditional power. Detection becomes biological. Some labs are even studying atmospheric ionization trail subtle disturbances in air molecules caused by fast-moving rotors as future sensing methods. This is environmental awareness. And here's the twist. All of this science exists because of drones. The need to detect small flying machines accelerated advances in edge computing, AI vision, RF analysis, thermal imaging, and distributed sensing. These technologies now power traffic systems, wildfire detection, wildlife conservation, and smart infrastructure. Drone hunting didn't just create defenses, it created new intelligence. It forced humanity to teach machines how to understand the sky, and the sky is becoming crowded. By 2030, analysts predict millions of autonomous aerial vehicles operating globally. Delivery drones, survey drones, inspection drones, emergency responders. So airspace itself must become intelligent. Future systems won't hunt. They'll manage, they'll classify, they'll coordinate, they'll predict. Cities will operate three-dimensional traffic control. AI will allocate flight corridors dynamically. Atmospheric models will route vehicles around turbulence. Buildings will broadcast navigation signals. The sky becomes software, but at the deepest level, this revolution is powered by physics. Electrons moving through silicon, photons reflecting off carbon fiber, pressure waves traveling through air, probability distributions predicting motion. The hunt is not for drones. The hunt is for understanding, because once you can sense everything, you don't need to chase. You simply know. And that is where 2026 takes us. A world where invisible systems quietly measure reality itself, where AI reads the sky like a living map, where machines interpret physics faster than humans ever could. And this is only the beginning. Next, we'll explore how quantum radar may see through clouds, how AI predicts motion before it happens, and how future cities will control millions of flying machines simultaneously. So stay with the series, because the future of flight isn't mechanical, it's mathematical.